Thank you for having me to talk. My understanding is that in the audience, there'll be some people who are new to Numba and some people who have some experience of using Numba and would like to know a little bit more sort of advanced things about it. So what I'm going to try and do is give something for everyone with a sort of overview and introduction to Numba, and then talk about some specific topics where people find it useful to know a little bit more about Numba. So some of those topics to do with specific problems with using Numba, and talking a little bit about the CUDA support and how to get started with it. I've got some material on sort of Numba's extensibility and embedding it as a compiler in other applications, but I think it might be a little tricky to get through to that today, but we'll see how things go. I'm hoping to leave plenty of time for questions, as Chris mentioned, and also feel free to reach out to me anytime. I'm always happy to hear feedback and help out with Numba related things as well. Although there's a few different topics that I have picked to talk about, there's a few things that I've decided to try and gloss over a little bit for today, just because it's hard to fit everything in. One is I'm not going to do a huge in-depth discussion of much of sort of performance analysis. I think it's just because I think it's a little tricky to do a really good coverage of performance analysis, and actually benchmarking Numba isn't something I spend a huge amount of my time on at the moment. I tend to sort of defer to users of Numba's benchmarks quite a lot of the time, and how they get performance with it. The other is comparing with other Python compilers. There's a lot of different Python compilers. LPython is another one, and helpfully the lpython.org website has a list of at least 30 Python compilers. There's a bunch of other things I've skipped as well. However, if there's things that you do want to know about, then feel free to put them in the questions and I'll see if I can talk about them. Chris has already introduced me a little bit, so I wasn't really going to say a lot more than him, just that I started out doing a PhD in the SPO group at Imperial College with Paul Kelly and David Ham, where I was working on PyOP2 and Firedrake. So things like solving PDEs with finite element method and domain-specific languages for HPC. I spent a couple of years working on more traditional compiler technologies like GCC and LLVM, and before I ended up at NVIDIA. At NVIDIA, I spend most of my time maintaining Numba and the CUDA target and supporting it for different sort of NVIDIA related use cases and broadly as well. So on to an overview of Numba. What I'm going to try and cover quickly is what Numba is, who uses it, and what do they use it for, and a bit about how it works as well. So what is Numba? It's a just-in-time compiler for Python functions, and it's not a compiler that compiles entire Python modules or entire Python programs. Instead, you would opt into using it just to compile the functions that you specify. Typically, the functions that you would use it to compile tend to be array-oriented numeric code doing lots of numerical operations. Rather than Numba supporting like the entire full flexibility of the Python language, it supports only a subset of it. The idea is that you're trading off some of that flexibility in return for getting better performance, and by opting into the functions that you do compile, you can kind of keep that trade-off in mind for those particular portions of your code. I think lots of people see it as an alternative to dropping down to using native code like C or Fortran, or compiling Python with Python, or using CUDA, something like that. Instead, keeping all the sourcing in the Python language. And at the moment, Numba targets a few different CPUs, so x86, PowerPC, ARM, and as well as the CUDA target. Because Numba uses LLVM, it would be possible to get it to target other CPUs that LLVM supports. Like, for example, RISC-V is an interesting one at the moment. It would take a bit of work to get Numba there, but I think that's theoretically possible as well. Who's using Numba? I kind of find it a bit tricky to characterize what a typical Numba user is. So what I tend to do is sort of point to the levels of usage of Numba instead. These are some stats that I actually grabbed quite a little while ago. Again, I don't want to put too much particular interpretation on these numbers, but I guess the signal that I take from it is that there are some people using it and finding it useful. What a couple of other analyses of Numba usage have been done as well. One is Jim Pivarsky, who used extended Numba to work with Orchid Array. I think he maintained a lot of other Python libraries as well. Did an interesting experiment where I think he used like a big AWS machine to clone all the repositories on GitHub that used Numba, and then did some quite interesting analysis on them to see what different bits of Numba they were using. So there's a link on the slide. In general, I've got a lot of links on the slides, and I understand that Chris is going to paste a link to all the materials that I've used today on the seminar page. So if there's links in here, then you'll be able to access them through the web page with the abstract. This is all on my GitHub as well, anyway. The other link I have is a while back I pulled all the projects on PyPI that listed Numba as a dependent and then sorted them by number of stars. So that list can be quite a quick reference to like what are the larger projects that are using Numba. Why are people using Numba? I think that one of the reasons that I hear quite a lot is that it kind of allows people who maybe aren't sort of software developers as their primary job function, but wanting to do other things like science and working in other domains, to keep all their code as Python code, but still get the benefit of higher performance, so that they can focus on like the algorithmic development aspect of what they're doing, rather than fiddling about optimizing their level code, making it a little bit quicker to develop what they're working on and maintain interoperability with the rest of the Python ecosystem. There is a question in the chat, which I'll come back to a little bit later at the end of the section, I think. So this is a sort of basic example of Numba usage, to using it to compile a particular function. It's not too important what this function is doing. Mainly what I want to sort of do is use it as an example of different features of Numba. So first of all, we're opting into compiling it by using the JIT decorator. You just decorate the function without JIT, and then when that function gets called, instead of it being run through the Python interpreter, Numba will step in and compile it and launch its compiled version. So some of the features that we're showing here are on the first line, empty or empty like. You can allocate new arrays inside compiled functions. We've got control flow like for and if and so on. For this loop, we don't just have to iterate over ranges of indices. We can actually iterate over elements in arrays or other containers. We can call NumPy functions, like numerical functions, like in this case is none. We can index arrays and set items and things like that. We can return arrays outside of compiled functions. And in this case, we're also sort of slicing and taking views of arrays as possible as well. So we're not returning the entire outer array, but just a sub array of it. In the next cell in this example, this is just a quick sanity check that the non-compact function does what we're expecting it to do. And then the final cell is a very quick sort of performance measurement, comparing the NumPy vectorized function or an implementation using NumPy vectorized functions on as opposed to the non-compact function. And what we see here is that the Numba compiled version is about 2.5 times faster for this very simple example. I wouldn't say that's typical or atypical. You can get much higher speedups compared to plain Python code, sometimes 10 times, sometimes 100 times, but it tends to be very dependent on exactly what the function is doing as to how much speed you can get and how much you change the way it's written as well, which I'll talk about a little bit later. I did mention it a little earlier on that Numba only supports a subset of the Python language and libraries in return for being able to compile all of what it does support for high performance. This is a quick overview of the key points. There is an exhaustive list in the documentation. I've got a link to that on the slide again. But basically, if you decorate a function with JIT, you can do all the usual numerical operations that you'd hope to do in operations on arrays. You've got all the standard control flow. You can raise exceptions and assert things. You can call other compiled functions, and we've got some partial support for generators as well. All the Python basic sorts of types are well supported, the tuple type as well, and some of the built-in functions as well. The main things that I point to that are not supported, and generally if you've got code that's written using these things, it can be a bit tricky to port to Numba, is catching exceptions with try except. We don't support. We also don't support context managers, and the comprehensions as well. Tend to need a little bit of a rewrite as well. In terms of the modules that Numba supports, inside the standard library, the mathematical ones that you hope to use. Again, there's a comprehensive list of other modules that are supported, but they're the main ones that I think about. In terms of NumPy support, there's been a lot of effort going into making the support for NumPy as large as we can possibly make it. So we support NumPy arrays, both of those containing scalars and structured NumPy arrays as well. The array should have attributes like shape and stride, and you can make reference to those. You can index into them in various different ways and slice them. NumPy scalars are supported and date times. There's a bunch of other functions as well that are supported. I'm just going to actually flip over to the NumPy features documentation because I think that's a little easier to refer to than trying to talk through the slide. So if I do that, then, oh yeah. So most of the NumPy types. Again, I'm just going to run through this really quickly. It's be a little tricky to read, but oh yeah, all the attributes of arrays that are supported are listed there. Various different calculation functions, lots of other NumPy methods. Just to pick a couple of random ones: ravel, repeat, reshape, etc. A lot of linear algebra functions are supported as well. Various different reductions, polynomials, another list of more functions that are supported. Just whiz past that quickly. Constructors for the different numeric types. Oh yeah, random number generation, so the generator API, and the old legacy random number generation as well. I think it's legacy now. And lots of ufuncs as well, so sine, cos, tan, add, multiply, lots of those as well. If you want to see what's supported, then you can have a scroll through, but I think the sort of general point I'm making is that there's quite a lot of NumPy support built into Numba. That's a little bit about what Numba is and what it does, and who uses it. I want to move on to talk a little bit more about how it works now. So first of all, the dispatch process, which is what happens when you call a function that's been decorated with @JIT. So when you do that, the CPython interpreter jumps over to Numba, and Numba takes over to try and compile and call the compiled version of the code. And the first thing it does when it wants to compile is to look up all the types of the arguments that you've passed to it. And the reason for that is it needs to compile a separate version of the code for each different set of argument types, because compiled code is typed, unlike Python code where there isn't really sort of typing in it as such. So once we know the types of the arguments, there's a cache, because Numba doesn't want to compile every single time you call the function. So if it's already seen these types of arguments before, then it can retrieve the relevant compiled version from the cache. If it's the first time seeing this particular set of argument types, it'll have to compile a new specialization, and I'll talk about how the compiler part of it works in just a moment. But assuming that we've now got our compiled version, the next thing it does is it has to unbox, because it's been given arguments that are Python objects, and they've got to be sort of marshaled to produce the native values that it can then pass to the compiled code function when it dispatches it. When the compiled code has finished executing, it's probably going to return a value. So then that needs to be boxed back up, which is marshalling it back into a Python object to pass back to the interpreter. So next, what happens in the compilation process? This is just a really high-level overview of how the pipeline works. Basically, we just take Python code and then translate it into LLVM's intermediate representation. And then we can leave it to LLVM to compile that down to the particular machine code that we're targeting, and then to sort of link it and load it as well so that it's ready for us to run. So a lot of the compilation heavy lifting work is done inside LLVM. We don't have to re-implement that in Python or in Numba ourselves. I think the heaviest lifting part that does happen on the Numba and Python side is type inference, which we have to do because the LLVM IR is all typed, but there's no typing in the Python source. So Numba roughly does type inference by propagating the type information from the arguments all the way through the data flow of the function until every single value in the function has a known type. I'll talk a little bit more about this at that point in the notebook, but I'm just going to switch over to a notebook now and then walk through that if I can find it. So all the notebooks that I'm using are also in the repository that will be linked. This first one, the life of a Numba kernel, the idea of this notebook was that I was aiming to show the pipeline all the way from Python to executing on a GPU. However, for the compilation pipeline, it's kind of it's basically the same pipeline for the CPU and the GPU. So I'm just going to reuse this, and the things that I demonstrate you can sort of think of as applying to any of Numba's targets. So throughout the entire notebook, there's this one function that I tend to use as the basis of the example. And the main things to note about it are we've got this area where we call a function CUDA.grid and assign that to I. So that gives us the thread index. We've got a conditional, which basically makes sure that we're inside the bounds of the array if our thread index is less than the length of the array. And if it is, then we'll do this computation. So as a quick test, I'm just going to execute those few cells and put the next cell, creates a little bit of random data and then calls the kernel using that data. So hopefully that's going to work. And then I've got an assert just to make sure, yep, that the kernel has computed what I expected it to compute. So everything seems to be working. It was this point at which we called the kernel, and then Numba's whole pipeline would have kicked in just there. So we'll work our way through what did just happen during that compilation. So the diagram here shows the sequence for the compilation pipeline. When we compiled that AXP function, called that AXP function and compiled it, the first thing that Numba did was use the Python bytecode compiler to translate it from Python source to Python bytecode. And that's really the starting point for Numba's pipeline. Some other Python compilers work with the Python AST instead, but Numba works with the bytecode. Once we have that bytecode, that's not quite enough to get all the way down to LLVM IR. So the first thing we do is this bytecode analysis step that turns the Python bytecode into Numba's IR. And the main purpose of Numba's IR is to get into a form where we can do type inference. And what feeds into that type inference is the types of the function arguments and the IR that we've just been given from the bytecode analysis. After we've done that, we've got this types Numba IR. And at that stage, there are some rewrites that can be done to the IR to optimize it a little bit in ways that are maybe tricky for LLVM to see. I'm not really going to go into those today, but just be aware that they're there. Once we have type Numba IR, that's in a fairly similar form, at least conceptually, to what LLVM IR is. So there's a relatively mechanical translation for Numba to just walk over the Numba IR and then map that onto LLVM IR underneath. Once we have the LLVM IR, we pass it to LLVM's JIT. We get machine code back, put it in the cache for later use if we need it, and also execute it as well. So for the remainder of the notebook, the idea of the notebook was to explain how Numba's internals work. And so at each stage, this just shows a little bit about what the internals are doing, and it shows what the code's doing as well. So first of all, bytecode compilation. I'm just using Python's bytecode disassembler here to see what the bytecode of the Python function is. And what we see is there's a sequence of operations in the Python bytecode. In the column on the left, that corresponds to the source line that it was from. Each of these is some relatively simple operation on some operand, and all the operands are kept in a stack. It's like a stack machine. So we can kind of see the corresponds to the first line of the code here, where we're sort of assigning, we're calling CUDA.grid with 1 and assigning that to I. We've got the conditional and the branch just here. So that's our starting point. I think I've mentioned all the relevant things I was going to mention there. Yeah, again, you can see what the computation is almost there, like the operations and the indexing and the arrays they're on. So we have the bytecode. We need to do the bytecode analysis to get to the Numba IR. And that's it, done with Numba's bytecode interpreter. Again, don't worry about too much about what the code is doing specifically. It's more the sort of general idea that I want to walk through. So once we've created the bytecode interpreter, we can then dump the control flow analysis that it produces. And it will give you a list of like adjacent, it will give you the adjacency list and all the stuff about the graph, which I'd never look at this representation because it's too hard to comprehend, even for something simple. So what I would instead do is have a look at the dot graph that it can render instead, and then we should be able to see the control flow graph in a much nicer form. Here we are. So basically, there's the we begin at block 0, and then there's 2 paths we can take. One is if the condition was taken, the other is if the condition wasn't taken. So you can at least see the structure of the control flow here. It's a little difficult to tie this back to the control flow, sorry, the original source right now, but we can see it a little bit later in the Numba IR when we get to that. The data flow analysis, you can also get that out of Numba as well. There's no good way to visualize this, but if you what it does track is all the uses and definitions in each of the Python bytecodes. So those 2 items would be used to construct the Numba IR. If we dump that, then what we get is something that is a little bit busy to read, but it's kind of like the we can still see some of the correspondence to the Python source code. So we've got the arguments RA, X, and Y. We've got the Numba CUDA module, and we're getting the grid attribute from it. Eventually, that's going to be called and assigned to I. So this, I think, sorry, let me scroll down and remind myself. Oh, right, yeah. Let's view it as a graph because that's a little bit easier to read. So again, we see the same kind of control flow structure, the initial block where we call I equals CUDA.grid of 1. And then we have the condition, and we branch, if we're in bounds, we branch to the block where we do the multiply add, or if not, we just branch to an empty block, empty-ish block. So this, at this point, we've got the Numba IR with its control flow. But the other thing I was going to mention is it's not the operands aren't on a stack anymore. Everything gets assigned to some new, uniquely named value instead. So that's a little bit easier to translate into LVM IR rather than the stack-based representation that we had from the Python bytecode. Oh yeah, at this stage we can do some rewrites, but like I said, I'm going to gloss over them for today. We're ready to do type inference. So I mentioned a little bit about the type inference before, how we start with the arguments, then we propagate the type information all the way through the function. And the way it does that is partly using the data flow graph to see where inputs and outputs are going. And the other thing it uses is some mappings of input types to output types for every kind of function and arithmetic operation and other operation that you could do inside a Python function. So the rules say things in code like, if you add together a float 32 and a float 64, then the return type will be float 64, that kind of thing. And it's fairly straightforward to propagate the information through the function when everything's a straight line. The main complication is when there's branching, when the control flow paths come back together again. You could have a multiple different possible types for a value, and you've got to do something about that. So we can explore that with this little example that just selects either A or B, depending on whether a value is larger than some threshold or not. So if we assume that we call select, where A is a float 32, B is an int 32, then when we're inside the if branch, the type of R is going to be float 32. If we're in the else branch, the type of R is going to be int 32, and that's fine for now. When the control flow comes back together at the return statement, we don't have a single type for R, but instead we've got a set of possible types, in this case, float 32 and int 32. So we have to do something to pick one type that will best represent the range of possible values of all the types that have been incoming. So in this particular case, float 32 and int 32 will unify to a float 64, the idea being that that should be the safest thing for retaining as much sort of precision of both the input types as well. That is, to some extent, a policy decision that's been made in Numba rather than a hard rule that you would always have to choose if you were developing something like this. You could argue for other, different ways of typing as well, but sort of trying to maintain as much sort of safe type promotion as possible is the safe and predictable is sort of the motivation behind the decisions made in Numba. So if we do have a function and it's had type inference run over it, then we can inspect what the results of the type inference are with the inspect types function. So this shows us the Numba intermediate representation again. but this time we've got all the types visible as well. So we know that we've got R was an array of int32, A was a float 64, and so on. We see the lines of the Python code. So I equals CUDA.grid. So we'll eventually see that I was an int. No, that's not right. Oh yeah. So where did we set I? Somewhere. Sorry, I'm trying to read this a little too fast, aren't I? Oh yeah, I set here, right? So I is an int64 because that call of CUDA.grid took an int32 and returned an int64. If you were trying to understand why numbers compile code a particular way, you can use this inspect types to function to generally tell what it's done with its type inference. If you want to know what argument types numbers seen before, you can use the overloads property. So we'll see that there's one set of types so far that we've called it with, where we've called it with int32 arrays and the float 64. If we were to call that AXPY kernel again, but with some different types, so all float 32s in this case, and run it again, we would then see there's two sets of different argument types, two versions being compiled in the overload dict. So now our float 32 variants are there as well. At this point, with the type number IR, we can generate the LLVM IR, and you can inspect that using the inspect LLVM method. So if I execute that, then it will print out the LLVM IR for the two different variations. I tend not to look at the LLVM IR because there's just so much of it. LLVM is really good at optimizing away all this sort of redundant code that isn't really needed. So what it allows us to do is simplify the development of Numba by just generating the code in the most simple way, and then LLVM will get rid of a lot of the unnecessary stuff, rather than trying to be very clever about our code generation, spending a lot more time maintaining that. So we have the LLVM, and then we can translate it to PTX. So there's two cells in the notebook. The large cell sort of emulates what Numba does internally. The lower cell shows the API that you would actually use if you wanted to see the assembly, which is inspect ASM. If I just execute the large cell first, then we get some. So because this was for CUDA, this is PTX assembly code. But if we were using the CPU target, it would be x86 on my laptop. What we can see at least is the actual code is a lot shorter than the LLVM IR. Most of it's been optimized away. But we can still see things that correspond with the original source, like the branch from our bounds check somewhere, the multiply add from the core of our inner loop. Like I say, if you are not interested in number internals, but you just want to know what assembly it generated, use inspect ASM, and that'll print out pretty much the exact same thing. So now we've got assembly out of that. It's over to LLVM or NVVM to generate the code. So I'm going to stop this notebook at this point because we've sort of reached the end of Numba's compilation pipeline. This is pretty much the point at which I was going to take a pause to ask if there are any questions. I see there is one question as well already, which says, are there any comments? Oh, so just while I think about this, if there's any questions that people have got up till now, please do feel free to put them into the Q&A, and I'll try and answer them now before I move on to the next part. So there's a question that says, are there any comments or tips on utilizing C++ modules written in PyBind 11 from within JITted Numba code? Is it possible at all? Unfortunately, I'm not familiar with PyBind 11, so I will find it tricky to answer that question. What I can say is that Numba does support CFFI and C types. If I can find that, let me find CF somewhere. So I don't know how much PyBind 11 gives you an interface. It's also if PyBind 11 has anything where you can sort of translate its interface into CFFI or C types, maybe that would be one route to using it. I just don't I just don't know enough about Pipeline 11 to answer the question, unfortunately. Are there any other questions at this point? Actually, if you want to send me an email, then I'll also see if I can find out the answer or paste it somewhere. There's another question, which is, does function caching in Numba differentiate between overloaded methods or treat them as separate functions? So the caching treats different overloads as separate functions. So if you were to call a function with one set of argument types and cache that, then that would be reused only for the exact same set of argument types. If you were to call for a second set of argument types, then you wouldn't get a cache hit from the first variant because the keys wouldn't match. So I think the answer is that it does differentiate between overloaded methods, and it treats them as separate functions for caching. I'll just answer live. Hopefully that answers the question. I think I should probably move on at this point. I don't see any other questions at the moment. So for the next section, I was going to go through a few examples of particular questions that I know have been sort of asked in the past to try to help make use of Numba. So I'm going to flip over to some notebooks for that. Oops, I can't get to the notebook because my Zoom thing's gone over my tabs. Let me just move that and then select that and maximize that. Right. So first of all, this first notebook kind of answers the question, how do you know when something gets compiled into a function? For example, have loop bounds been compiled in or not? Secondly, what if they are if they're not compiled into the function, is there anything you can do that would make them, that would force them to be compiled in? So after a quick bit of setup on this in this notebook, I'm just going to import Numba. We've got this very simple example function. It's got a loop. That loop has got some bound, and the bound is defined externally to the function. Now, if I then call that function with the example data, I should get a result back in a moment. Okay, and then the inspect assembly function that I mentioned briefly before, we can use that to see what actually came out. So if we look at the assembly, what we can see is that, well, in some form, the constant 100 did get compiled in this case. It's actually minus 100 because I think somehow the loop got rotated slightly somehow, so that rather than the constant being 100, it was minus 100. But the point is there's a static bound in there rather than it being a variable. Now that was because that happened. Well, one explanation for that happening is that n was a constant from outside the function, or seemed like a constant from outside the function. What if we didn't have a constant, but instead we had some variable loop bound, like the length of the array that we pass in? So if I execute that and then dump the assembly for it again, this time we see there isn't a constant in there. The code for the function is also a little bit longer. Instead of having that constant, we've got some stuff, some code that's instead looking at what the loop bound is actually going to be. And the code is generated slightly differently. Although the body of the loop is the same itself. So yeah, there's no constant 100 there. The length of the array is dynamically used. So could we force that to be compiled in? And one way you can force things like bounds and things like that to be compiled in is to use this literally function. So this time we use the range and the literally function. What I've actually had to do here is pass in n as a separate argument and then take the length of x and pass it in. So when I execute that and inspect the assembly, we can see we've recovered the original version, even though we're using the length of the array where we've got the hard-coded constant in. So what happens when we use this literally function is that it forces Numba to see if it can get the literal value of n. And it does have it available at compilation time because we've called it with the length of x, which has returned the value. So it can make that into a literal and compile it in. That's kind of a little bit inconvenient because it's not exactly how you'd like to write your code. It would be better if you could just say literally length of x. At the moment, that's not quite possible. If we were to attempt to do that, like here, we just say literally length of x. And what will happen is we'll get a trace back and it will say, I can't literally give you an int 64. The reason is that to be able to do that, Numba would kind of have to call length of x at compile time to get the length back, to get the literal value. And I think it could be possible to improve Numba so that this is possible. Maybe it should outline len of x, JIT compile it, get the result back, and then compile it into this. I think it'd be a lot of work to do that. So at the moment, you have to use this workaround from example 3, where you pass in the length and then literally that. The next notebook, okay, oh, there we go, was kind of along a similar sort of theme. This is to do with capturing globals and closures. So there's this, there is a section in the documentation Numba that talks about deviations from Numba's Numba's deviations from Python semantics. Talking about global variables that you refer to or closure variables that you captured, they get frozen. So it sees the values of those variables when they're compiled, and then it bakes them in. So then you can't change the value after that. The documentation is a little bit maybe ambiguous with some, don't want to say weasel words, but some words in the documentation make it hard to tell what it's going to do. So I'm going to try and make that concrete a bit with this notebook. So again, with a little bit of setup, and then if we generate some random data, so I've got some values and some indices, I'll JIT this function, and what it will do is if you pass some value in, it will return the index and then the value that is indexed by indirectly there. Call it, should get some value back. And then if we look at the assembly for this, what we would see, if I scroll down, tends to be towards the bottom, is that we've got the array data. The data for those two arrays has actually been compiled into to the function. So when you see const array data, so const array data is one of them, const array data.1 is another. When you see this sort of thing, that's when Numba's copy the data in and compile it into the function. One of the problems you can get with that is that if you then modify this data outside the function, it doesn't have any effect. So if I change the indices so that that index that I used, instead of being 6, it's 4, so I'll just do that. If I call get value of 1 again, I should expect to get back 4 here and a different value. But instead, Numba's use the old, or the Numba compiled code has still got the original value from when it was compiled. Like, you might also think if we're compiling data into a function just because it's a global variable, if you have a really large array, that's not going to be very sensible. So at some point, Numba actually switches over and doesn't compile things in anymore. So if I make my data 10,000 long instead, and then compile it, what I'm sort of showing here is that the point at which it switches over is still quite large. If I scroll through this, I've now got tons of assembly with loads of baked in values. I'm not going to scroll through all that, but if we make it a couple of orders of magnitude larger, and then inspect the code, finally we see we've got a nice short code again because the globals haven't been baked in. If it's made these references to what it calls dynamic globals, instead you'll see references in the code to Numba dynamic globals rather than const array .n for some n. So those are the different behaviors that we've observed. What are the rules that are actually governing this? And I looked this up just in the Numba source code to find out if your array data is less than a megabyte and it's contiguous, then it will be baked in. So you could prevent it by baking in by making some data appear to be non-contiguous or adjusting the typing so that you have a type for a non-contiguous array. In terms of the CUDA target always tries to bake things in, and I think that's a wrong behavior, but something I'm hoping to fix for the next release. I just have one other notebook which talks about another topic, which is sort of how to approach using NumPy functions, because you can call NumPy functions on an entire array, or you could rewrite the function that uses these NumPy array functions in terms of for loops and scalars instead. And there's various reasons why you might prefer one or the other, but with this notebook, I want to try and explain some of the considerations when you're using Numba. So again, I've got a little bit of setup in this notebook, and just to create some data. Then let's suppose we've got this function. So the function takes an array, it does some stuff with that array, it squares it, and then depending on what the values of the array are, it does one computation or another. And then again, data dependently, it does something, it picks one computation or another. All of these sort of array operations. So if I just execute that, this is just a pure Python version executing on the data. So it takes nearly 6 milliseconds. What if we compile it with Numba? Before I do this, what I am seeing is that now that I'm running Zoom, it seems like my laptop's a lot slower, so I'm not quite sure what I'm going to get here. But oh yeah, sorry, I forgot to time it. But hopefully the results I'm expecting won't be too different from what I get. All right, okay. So we jittered that function, and in this case, it's actually been a little bit slower with Numba. And the reason for that is that in this function, there's not a lot of interpreter overhead because these NumPy array functions are all dropping down to C anyway. There's not a lot of interpreter overhead because there's only one sort of function call for each of them throughout the entire function. So yeah, that overhead was like unboxing and the dispatch process. So what we could do instead is rewrite that function using loops and scalar operations. So we loop over the length of the data, and then the computation is written just in terms of scalars instead. So we pick the ith element of the data, and then we use conditionals, control flow structure rather than NumPy where to select which computations we do. And one of the things that this helps with is it saves you doing as much computation, because if a value is not needed, if one of these branches isn't needed for a scalar, then it doesn't get done. First of all, it's not obvious to me just at a glance that this does exactly what the other function did, but I've got a check in the notebook that checks that it does seem to be doing the same thing. I did try it initially with np.testing.assert equal, but I found that this did produce a few ULPs difference. And one of the reasons that could be is because the NumPy might be built to call a vectorized math library underlying, which might make these slight differences. So I've just checked with all close rather than equal, in case you're wondering why I did that. So this pure Python version of the function that uses loops and scalars is way slower than the NumPy vectorized version. The reason is we've added a ton of interpreter overhead because it's now doing the for loop inside the Python. So that has slowed down the Python quite a lot, CPython quite a lot. If we compile that with Numba instead and then time it, hopefully, okay, so that variant of the function is about 2.5 times faster than our original unjitted function. So by rewriting that loop into that function in terms of for loops and scalars, we've managed to pick up some performance. So basically, to summarize, what I think the lessons here are is if you've got a function that's vectorized already, it can be straightforward just to JIT compile it and see what you get, but it can limit the amount of speed up that you get from Numba because there's not much interpreter overhead to remove. If you rewrite the code using loops and scalars, that can improve the JITted version because it means that you don't have to allocate so many intermediate arrays, and it reduces execution time when you're sort of avoiding doing computations on unneeded branches. In general, I think the more complicated the function is, the greater the potential speed up can be because you're kind of cutting away more and more efficiency for each of those operations. And I tend to find it easier to read those like for loop and control flow variants of the function more easily than the complicated vectorized expressions, but that might be different for different people. I guess one thing I'd say is if you planning on using Numba as an optional dependency for speed up, if you do rewrite your code using loops, then that can slow down your pure Python version a lot. So you might want to be mindful of that. You might need to keep 2 versions of the function if you plan on making Numba an optional dependency rather than a hard dependency. The other thing to keep in mind is Numba. I did show a lot of NumPy support in the support list, but not every function is supported. Sometimes you need to rewrite a NumPy function in terms of some other functions, or you need to rewrite things just to get it to compile. In that case, you don't have much of a choice. So that kind of sort of finishes the section. Yeah, so that sort of finishes the section on those sort of development tips. Again, I wanted to pause for questions. I see there is a question. Again, while I have a quick look at this, if there's any other questions that you have, then feel free to send them. But for the first question, it says also, if you rewrite the loops, you'll lose the vectorized syntax and it'll prevent you to test other acceleration frameworks like CuPy or TensorFlow, maybe a drop-in replacement for NumPy. Yeah, if you do have, if other compilers work better with that vectorized syntax, then yeah, it will make it a little more tricky. In the case of CuPy, you might find that CuPy's JIT could also compile the function. I think that it doesn't have as broad support for everything in its JITted kernels. Well, I think it's fair to, sorry. The sort of the overlap of CuPy and NumPy JIT support it's not sort of like exactly the same set of things. So it may or may not be that you could also compile that with CuPy's JIT. Again, if the other thing I'd say about CuPy is you can use CuPy in conjunction with Numba's CUDA target. You can use CuPy arrays and you can write Numba kernels, and you can call the Numba kernel on the CuPy array. So they mix it fairly seamlessly. So that can also be a consideration.
Brilliant. Can I ask you a question? Because I can't actually type that. So a couple of things that just sprung to mind. When you're using that literally syntax, does that cause it to cache a different version for each different literal that you put in? Because presume the
yes,
right. So that's cached.
Yes, sorry, I totally forgot to mention. If you use literally, every different literal value is a different variant, because it's you can't reuse like the literal loop bound 50.
And the other question was, when you have those tables of data which you're referring to either baked in or as references, in the second case where you've got a huge table and it's a reference, can you then change the data?
I would think so.
And it will be, so that seems more flexible. I think, why isn't that the default?
I think originally it was done for I think originally Numba didn't have any sort of like reference counting and garbage collection, so it wouldn't be able to track references to arrays that were outside of the compiled function. Maybe you're making the case that that default ought to be either changeable or at least customizable. So I think so I think making that a bit more controllable, maybe even the default, is worth some serious thought.
Okay, thanks.
Okay. I noticed that we're sort of coming to the point where I've been going on for about 45 or 50 minutes. So I just wanted to take your input as to whether to carry on a little bit, spending a few minutes talking about the CUDA target, or whether to sort of wrap up here, or what do you think?
Yeah, I think that's good. Carry on for a bit more. We're okay for time. I think it's okay as long as people can just drop out from the call if they want to, but I think we're all happy for it to carry on.
Okay. All right. I'll oops, not focused on PowerPoint. Yeah, so I'll try to be brief about the CUDA support. So Numba supports the CUDA. It has this CUDA target as well. Initially, that was sort of a closed source add-on to Numba called Numba Pro, but then it was open sourced in 2014. So the CUDA target's just built into Numba at the moment. In order to, because the GPU is sort of a separate device rather than something that's like just there like the CPU. The CUDA target has a few different components. So one is the JIT compiler targeting CUDA, but then it's also got some bindings for the CUDA driver API built in, a little bit of sort of minimal device array library built in, and then support for something called the CUDA array interface that I was kind of alluding to just a minute ago, where those all the different libraries in the CUDA and Python ecosystem follow one or two standards, like one of which is the CUDA array interface. That means you can use these libraries all together and compose them with using different, you can pass one library's arrays to the other, for example. There's I'll just skip over the list of users. I think what I'll actually do, given the way time is, I think I'll go to the notebook first, and then I'll start to talk a bit more on the slides if there's anything to if there's more time after that. So I have this notebook that gives a very brief overview of the CUDA functionality. First of all, should you use Numba and CUDA? Not absolutely everything is going to translate well over to a GPU. The things that do work well tend to be numerical code, loops, where you've got large amounts of data, lots of data parallel operations. Then they're the things that are going to tend to sort of port over well to a GPU. Things that are not going to work so well on CUDA are things that are using lots of strings or dicts, for example. Things where they're sort of very complicated data-dependent control flow, or code where you've already got lots of object-oriented patterns and features. They can be a little bit more tricky to port to CUDA. So those are the sort of general guiding principles I would think about. I mean, theoretically, you can port anything to a GPU. How hard is it to make it run fast, I guess is the question. This is just a super brief overview of CUDA. So the GPU hardware is separate from the CPU. It tends to have its own separate memory, and it's accessible over something like a PCIe bus. So when you're using it from Numba or any other programming system, you tend to want to send all your data over to the GPU, do all your computation on the GPU, and then get results back, rather than having much sort of back and forth of data between the CPU and GPU. It's much more efficient if you can keep all your data on the GPU and use it there. In practice, what does a GPU look like? Instead of being a smaller number of cores that operate very fast sequentially, it tends to be a large number of cores that execute a large number of threads, and they all do that in parallel. In terms of the software view of that, when you call a function on the GPU, you would launch an entire grid of threads. So the grid, one grid executes one kernel. That's broken down into a set of blocks, and each block contains an individual thread. And all these threads and blocks have their own indices, and you would use those indices to figure out your place in the input data to see where, to figure out which items of data the individual thread is operating on. I'm sorry, this is such a super quick overview of CUDA, but I hope this gives just enough basis to sort of follow the rest of the notebook. If you've not used CUDA hardware before, there's a few options if you want to tinker with it but not invest too much of your own money or time setting things up at the moment. One is you can use Google Colab to get access to your GPU. If you go to colab.research.google.com, fire up a notebook, and then if you go to runtime, change runtime type, you can choose hardware accelerator and change that to GPU. So for free, you can usually get access to a T4 GPU. If you want a fancier GPU, and I think there's V100s, A100s, and L4s if you have a paid account. It's good in the sense that it works with Jupyter notebooks. If you work well with Jupyter notebooks, then that's quite convenient. If you're not a big fan of Jupyter notebooks, probably maybe not so good. The other option you have is to put a GPU in your own machine. That will be consistently available to you. You can install and run any libraries or software versions on it that you want to, and you can use a debugger if you want to as well, and other tools like Compute Sanitizer. The con is you might not get as good performance as if you use someone else's big expensive GPU. You've got to sort of set it and maintain it yourself. If you did want to just get a very basic GPU for getting started, I had a look recently. It seems like the GTX 1650, you can pick one up for about £150, which seems like the simplest starting point. It's good enough to get going for development, make things work. And if you have found that's worked for you, then you can think about moving the code to a higher performance system later. Maybe also you could use an HPC system you've already got access to, depending on sort of how well it can work interactively for you to sort of test things out and debug and the usual sort of batch submission stuff. There's cloud services as well. I haven't personally looked into that, so I'm just going to move on from that. So this, the rest of the notebook is just a very simple demo of a diffusion code, starting out with the Python code and then moving to a parallel CPU code and then the CUDA target. So initially, just a bunch of setup and testing to import Numba and the things we need. Make sure that CUDA seems to be working. Yep. So this is a little example of sort of like a diffusion of a hump of tracer for some number of iterations on some size grid. So the first cell, I'm just going to set up the initial conditions, a Gaussian hump, hopefully. It takes a long time to generate this if you don't JIT it with Numba, so I'll just use the CPU target to generate that. And there we are with our initial conditions. The Python version, it's just a dead simple stencil function that is going to smooth things over using the neighboring points, swapping between two buffers on alternate iterations. So, not actually going to run this because we'll be sat here for minutes waiting for it. I've commented out the code to run it, but if you grab the notebook later and you want to try it, you can just uncomment this. And then for the CPU variant, we JIT compile it and also use the parallel equals true argument so that Numba will compile for parallel execution. So to tell it what to parallelize, you change your range decorator for p range. So I've parallelized the outer loop here. Other than that, the code is pretty much the same as the initial Python version. So if I execute this, then hopefully in just a moment we should have a result, not too many seconds. I think my laptop's doing 95% zoom and 5% Numba at the minute though. Well, this might make it look like a very good argument for using the GPU instead. Yeah, just while it's running, I'll start talking about the CUDA version because we modify things a bit more for the CUDA version. Instead of the njit decorator, we changed that for CUDA.jit. We've got rid of the two for loops. Instead, what we've done is distribute the iterations of those for loops across the grid of threads. So each thread takes one iteration instead. Then we get hold of our indices, I and j, using the CUDA.grid method. If we tell it 2 is for a 2D grid, so our two loops have been replaced by the 2 dimensions of the grid. You can launch a bigger grid when you have data, and often it makes sense to do that in certain ways. So we've got these checks to make sure that our particular thread is still within the bounds of the grid. We don't want to access data outside the grid because that will be invalid. Sorry, grid, the domain, the computational domain. And then the for loop sort of turn into this if condition. If I and j are in bounds, then do the stencil. We've also modified the code that launches it slightly so that we transfer the data over to the device before we execute it. And we have to figure out what the size of the grid and blocks are. These are just sort of based on the size of the domain. And then we can call that function. I'm just wondering if at this point, if the CPU, the CPU version's finished running and the tracer's a bit diffused. So hopefully if I run the CUDA version, it shouldn't be too long to get a result. Oh, there we are. That's diffused as well. So then if we compare the results, there is, well, not a super exhaustive check, but it appears that there's no difference between the CPU and GPU outputs. And then, okay, that took almost a minute on the CPU and 4 seconds on the GPU in this particular example. That's, I think what I was seeing before I was running Zoom was that the GPU was about 10 times faster than the CPU on this machine. So that might be slightly exaggerated, but still maybe within some kind of same ballpark results. That's the end of this notebook. There are a few other resources linked in the notebook about using Numba with CUDA. Oh yeah. So what I think I will do just to round out this section, rather than going exhaustively through all the features that are supported or not supported, I'll just mention that there are a bunch of CUDA functions that you would normally use inside kernels that are in CUDA C and C++ that are also available in Numba. Not everything's there, but all the main ones are there. There's some host-side APIs as well that you use for launching kernels, for controlling concurrency, for recording events and sort of synchronizing things and timing things, and managing memory on the GPU and different devices as well. They're all available in Numba as well. This CUDA example. I know we've just seen a CUDA example, but this is just another instance of the general pattern. If you have a function in Python, then generally the pattern you use to change it to use CUDA is to add the CUDA JIT decorator and then distribute your loop across the threads. So in this case, we might have more work items than there are threads. So what we do here instead is sort of still have a for loop, but it's strided by the size of the entire grid, and then launch that with an appropriate size grid and block. There are some tools that can help you when you're developing code using the CUDA target, which I'll just make a quick reference to them. I think the main thing is to be aware of them so that you know to sort of use them and look them up. One is CUDA GDP, which is often used for debugging CUDA C and C++. It does work a bit with Numba's CUDA target in the sense that you can break in kernels, you can step through lines of code, and you can see the Python source correlated with the with where you are. You can also disassemble the GPU assembly code and step through that as well. At the minute, it's a bit tricky to view data on the GPU, but if you've got some kind of, sometimes this can help give you a little bit of insight into what's happening. It's not the first tool I would reach for debugging CUDA code, though. The other option is the CUDA simulator, which is built into Numba, and it simulates this execution semantics of the GPU just inside Python with a lot of threads. So the advantage of this is it means that you can just step through your CUDA code just like you would normal Python code with any Python debugger. I use PUDB, but PDB would be okay, VS Code would be okay. You can set breakpoints, you can inspect variables and things. Like I say, the main problems with it are it's very slow because it's just simulating a GPU in CPython, and it doesn't quite support everything the actual CUDA target does. There's another tool. Oh, right, yes. So there's this profiling tool for GPUs called Insight Compute that can give you a lot of different metrics into CUDA kernel execution. It was written for CUDA C and C++. Because Numba can generate line info, you can use it with Python kernels as well. So what I'm just showing in this here is how in the column on the left there's the Python code. You can see for each line of the Python code it's correlating all the metrics for the that it's measured during the execution of the kernel with the individual Python source lines. So you can use this to optimize performance and understand where the hotspots in your Python kernels are. The other tool is compute sanitizer, which is a bit like Valgrind for GPUs. If you have memory errors where you're accessing out of bounds, it can detect them very efficiently and then tell you where the problem is. So in this example, I've got a jitted function. I've got an off by one error. This check if we've gone off the end of the array, that should be greater than or equal to x.shape, I think, something like that. So the last thread is going to just write past the end of the array. When if I had debug equals true, Numba will generate debug info. If I run this under compute sanitizer, I'll very quickly get a message from it telling me that, well, I've got an invalid global read because I was trying to increment that. I had to read the old value. It tells me what the Python source file name was, what line it occurred at, and which thread did it, and what the name of the function was as well. Although it looks a little bit mangled because Numba sort of mangles the name a bit when it compiles it, but you can see it was this add one function and the types of the arguments as well. That's kind of the end of the CUDA section. I'm wondering if now is a good time to wrap up and take questions. I think diving into the extension will take a significant amount more time to do it in a meaningful way. So I'm leaning towards sort of opening to questions and discussion here. Again, I defer to what the organisers think, though.
Sure, I guess it is a good time to wrap up. We've just been about an hour, so yeah, if there's any more questions. Okay.
While people are thinking about questions, this is my sort of wrap-up slide. If you want to try out Numba, you can install it with Conda if you use Conda. If you do that and you want to use CUDA, then you can add these extra packages as well. Or you can install Numba with pip. There's the link to Google Colab if you want to try that. I mean, you can use Numba for the CPU target on Colab as well if you don't want to install it locally, or the GPU. These slides and notebooks and everything for this talk are just here. And also, if you look, there's a bunch of other, you can download the slides. There's a bunch of links to other resources for all sorts of different things as well to do with Numba. And yeah, just wait and see if any questions come in, I guess. In the meantime, thanks for your attention. Thanks for having me to talk to you.